Hello and welcome to week 2 of Big Data Analytics for Business. This week we're covering, let me grab the book, this book right here, chapters 4 and 5, and a few other miscellaneous things. So hopefully you're doing well. Those of you that emailed me, hopefully I got back to you and we're all doing well. So let's dive in a little bit. Okay, so just to recap what we did last week, the first week. We went over the syllabus, what the expectations are. You're allowed to use ChatGPT in this class only. I gave a week by week kind of plan, the books, things like that. The number one or number two things that you really had to do with the discussion post. The discussion post is generally it's a way for me to engage in the class. I've taken online classes both at UNLV and outside, and a lot of times they're just a bunch of videos, and I don't like having a bunch of videos I can watch one after the other. I think that type of disconnection between other students it doesn't work. It doesn't create that bond. So that's one part of the discussion. Another part is to think kind of critically outside of what's right in front of you. We can't, especially as a university or any educational institution, I can't teach you, I don't feel, that I can teach you to do X, Y, and Z, X, Y, and Z. I can't teach you just a program, a programming language, a software tool. If I teach you one of these things and you know it verbatim, what happens when it changes? What happens when it changes? Then your knowledge is no longer valid. So that's why I want to teach you kind of to think, to research, to kind of interrogate. That's kind of what the discussions are. There's two quizzes. They're super easy. I'll tell you the answers. The answer is yes to all of them. One of the quizzes says, hey, you read the syllabus, and the other one says you have the tool set up. The quizzes aren't there for me to challenge your knowledge. The quizzes are there for me to say, hey, you have all the software set up. You have this done. Normally I just have a homework assignment, you upload, say it's done, but there's so many people in this class, this is one of the larger classes I guess in the graduate college, that it's just easier for me to do quizzes. If you hit yes, boom, it's easy, you're fine. Also next, there's a thing here, let me actually edit this here. I just wanted to add a deadline to that. I believe that whole SMART, specific, measurable, and I didn't have a time on that one, so that's one problem. But there's a supercomputer tour, NCSE. There's a tour of this facility. It's not the world's biggest facility, but it gives you kind of a better idea of maybe what a supercomputer looks like, what these clusters look like. I mean, what is a node? How does memory kind of fold between the two? So I don't even know if these are still around. These used to be dev nodes. I have a cluster at my house. So sometimes it helps to see it, sometimes it doesn't. If you want to go, there's no extra credit, no nothing, but it's at SEB, UNLV SEB. So it's this building right here. We'll meet downstairs, either right in front of Starbucks or somewhere. It is February, let me look. It is February 9th at 1 p.m. I have 5 people going so far. So if you can respond, just let on that doodle poll, or something, it's a doodle thing, by this Thursday, I would appreciate that. Again, I want to thank the people who cited OpenAI or Chat or BERT or whatever auto AI tool they use. If you use it, even for spell checking and for low-hanging fruit, please just say, hey, use ChatGPT or use OLAP or use Copilot. I mean, there's so many of them nowadays. Use Claudia. Just put it down at the bottom. I'll be happy. That way, if the university ever says anything, we're both okay. So please make sure you always cite it when you use it, either in discussions, in your homework, and in your code. Anywhere you use it, just cite it. Today, we're going to go over chapter 4 and 5. I'd much rather be in much funner stuff, but the fundamentals are very important to get into. So we're going to go into the fundamentals. Then we're going to just talk about the discussion post. Everyone's discussion post was fine. And then it's not really homework, but I got a job offer this week, and I want to talk about it because it specifically mentions big data. So I want to kind of talk you through the logic of that, and I just want to make sure everyone's able to contact me. And if I don't respond to you within 24 hours, email me again. Normally I get to all your emails right away, but sometimes it doesn't happen. Or text me. If I don't text me and it goes into my like unknown senders or unknown receivers on my phone, just text me again or email me. Nothing should take me more than 24 hours to respond, if not sooner. So let's dig in a little bit. You know, data is information, or processed data, refined, clean data is information. Cleaned information is knowledge. Now, I like the word process or clean, but process or revise or summarize knowledge is wisdom. You just kind of think, what level am I working at? Am I working at with information? The data set's been clean, things have been organized, but really no actual intelligence. So this is where we're kind of going. You're taking raw ones and zeros, adding information, adding information, adding information. I'll go into a couple examples of this here in a minute or two. Okay. Now, this course is not designed to go a ton into databases and these two different types of, I just realized this is over. Oh, I guess that's fine. Sorry, I was going to adjust this here. It's driving me over the wall. There we go. Okay, so this class is not really designed to go into different types of database and a ton of database stuff. I did post on this week's module. Get to it real quick. This is just a recording from last semester, which I go into a lot more detail on ETL, the transactional processing and online analytical processing for databases. Just the first 20 minutes, it's optional. It's only if you want to dive a little bit more into the different types of database. Now, SQL or databases are one of those things where you can spend your life into it. Let me... Okay, so in the world of SQL, just like anything, there's this huge continuum from people that have very little knowledge to like super complex knowledge. I personally think I'm down here. And I think the reason that is just because I work with a lot of DBAs that do nothing but work on databases. I work with a lot of people that do nothing but write SQL queries all day. And every day I'm in SQL, every day I'm working and writing queries. But my queries are relatively basic, okay? They do summarization, they do a lot of filtering. I think they're very basic. But just having this, level of knowledge somewhere in here, middle ground, I would say is probably one of the most valuable tools. I didn't realize how valuable SQL was going to be until I really started working with machine learning. Now, why? Because so much data is online in databases, and not only that, if we kind of go down, the data that's online, sometimes it's in Microsoft SQL, sometimes it's in NoSQL, sometimes it's in MySQL. Data is never in one place and very easy to get to, readily and easily. So having a fair understanding of SQL is vital. So if I was to ask you, hey, write, here's a database, write a script to give me all the roads that lead to, or all the roads that have the word rainbow in it. You got some type of database of all the streets named in the United States. Every street in the United States, there's got to be some database out there that has that name. The post office probably has it. And I want to know all the cities that have a road named Rainbow. Where, road name is like or contains rainbow. Put little, what dollar signs, or not dollar signs, shift 5 before and after. Okay, that's good. Well, I want to know all the roads that have roads, I guess, longer than 5 miles. Hey, where a length is greater than or equal to 5 ml. Maybe it's a string, and you have to convert it to an int. These are just basic database things. Now, like I said, it's one of those things where, hey, databases are super important. I'm not a big database guy. I work on them every day. I write SQL every day. It is super important, but I'm not going to tell you, hey, to go out and spend your life becoming an SQL expert, becoming a DBA. I mean, for 99% of what I do, I have read-only access on databases. So, anybody should be able to sum, average, filter years, things like this. And when I talk about the job, I'll talk about databases a little bit more. So, big picture is there's online transactional processing type database and analytical processing type of database. Now, these are sometimes hard to comprehend. Let's see what the next slide is. Let me go back one. But in a nutshell, this a transactional processing is a type of database that basically just grabs everything. Maybe every record, every sale, everything you do, that's what's in there. Now, what happens a lot of times, we summarize that into analytical processor. We summarize it into a data mart. Okay, now think about this. If we're doing our taxes, because it's not quite taxes, but it's coming up in tax season, a receipt or your bank account has every transaction that you did. Here's my credit card. It's a great example. Oh, good, you can't see the back of it. Okay, so my little credit card. Okay, so I go and buy something. Boom, I go and buy something else. That's all on a log here. Now, if it's tax deductible, I have to summarize all that information. I have to take all my transactions and analytically summarize that to something that's logical. Hey, I spent $10,000, $5,000 of it was a deduction. So that is the logic for moving here to here. Okay, so a data warehouse and a data mart. So let me try to explain the difference of this. A data mart is where we take a database or a collection of a lot of databases and kind of summarize them together for informational purposes. And a lot of times we'll take traditional data marts and kind of maybe summarize a bunch of them together to a data warehouse. Boy, that was confusing a lot of times. So I have all these banks, and all the banks here in Vegas. Let me step back. My bank here in Vegas is on Pecos, I think. I don't know where it's at. Pecos and maybe Flamingo. Well, they have every transaction that I have that's stored in a database. Well, maybe that database needs to be aggregated because the bank, the regional manager or the manager of Las Vegas wants to know, hey, how many people how much money did we spend yesterday? How much money did we take in? So they take all those transactions, kind of concatenate them, and move them to a data mart. And they say, hey, for January 22nd, all the customers spent $5 million, and we took in $15 million. So that at some type of regional level is a data mart. It doesn't have to be regional. It can be per business. It could be per anything that makes sense organizational wise. And we take all that information, all those data marts, and combine them to a data warehouse. And I have some graphics that will help explain this a little bit better, because once you kind of understand these terms, things make a lot more sense moving forward in databases. And their book also mentions traditional BI, which to me is just looking back at kind of what happened and trying to make sense of that. How much money did we spend last month? What taxes do we owe in Q3? Things like this. So I kind of love this image. I used it last year, and it makes so much sense to me. Okay, let me see if I can switch over here. Okay, so we have, I don't know, maybe a restaurant, something, a car dealership. There we go. Well, we have a lot of different databases. We have all the employees in the sales. Hey, John made X, Y in sales. Marie made X, Y in sales. Now that we have janitors, we pay all types of things. We have all these vendors like AutoZone, where we buy parts or whatever. where we owe, $500. We owe Chevy, I don't know, $5,000. The billing system, so we have all these, we have a Visa. Somebody bought a, I don't know, a Visa card for $82,000. We have all this different kind of data. And now, as a manager or as a business professional or as a leader, pick a word. I don't care about all that. I don't care necessarily about who made what. But maybe my question is, how much in commissions, commissions, did I pay last, well, let's say Q1 versus Q2. Is there a color of truck that sells better? Okay, so now this one is really, let's say, super easy. We just take all the sales of all the vehicles. So maybe we have 500 sales a quarter. Then what we're going to do is we're going to aggregate it. We're going to say, hey, maybe we sold 500, or let's say 100, sorry, red. Let's say 50 black. That's 300 blue. So we're going to extract all this information, basically concatenate it, summarize it, do something, and store it into another database, a data mart. Okay, we're going to store it into some type of system that is kind of aggregated. Remember that quote? We have processed data. So this is how that kind of happens. So instead of looking at every sales receipt for the last 3 months or last year or last 10 years, I can just go to this new system and say, hey, look, everything's here in a nice clean order. I just need to know X, Y, and Z. And it makes life a million times easier. Okay? And like I said, it's really important that kind of we understand this idea. We're going to take some type of raw data. This system's designed for fast processing, designed to capture as much of the data as it can. It's weird that this date's not right, I just noticed that. It's going to capture as much of the data and ensure data availability. We're going to do something with that data, sum it up, do an average, do something. Then we'll store it a lot of times on a data mart or more aggregated system. This is maybe your checking account or your bank register. This is your taxes. It's really that simple. Okay. Handles a lot of small transactions, handles complex queries. And a lot of times too, in between here, let me switch over here. Sometimes there is like software that does these, that aggregates it. Sometimes there's not. Sometimes the database itself will summarize it. Sometimes it's just a straight aggregation. I mean, there's a million different ways to get to this. As long as you understand the general idea, this is designed for a lot of small, this may be like, if you think about it in your head, for a computer person, SSD, and this may handle, HDD. Well, that's not the best example. It's one way to think about it, So, the analogy I came up with, I think, with last semester, this is actually a slide from last semester. If you look at my whole life, maybe I've eaten at McDonald's 1,000 times. I'm not really sure. But let's say I've eaten at McDonald's 1,000 times. Oops. Maybe I've had 860 Big Macs, 900 fries, whatever, blah, blah, blah. Now, if somebody was going to say, hey, I need to put an order in for you, or do you want anything from McDonald's? They just need to know that, hey, 85% of the time I eat a Big Mac. The average price is $5, so I can give you $5, and I like extra ketchup, which I don't. And boom, this is a raw data. This is knowledge. Somebody can buy me lunch. If I'm working in the lab and I need lunch, this is actionable intelligence. This is raw data. This is just a little slide that I found. I still like it. Insert update, select, response time milliseconds. I mean, on some of our data marts, we run queries that take, I always try to limit query times, but some of our queries run 2 or 3 hours. I have a query that I run today, Sunday, and it takes about 4 hours for one of them, about 6 hours for another one. Now, I would never run that on a production server like this. I only run it on a data mart because it's designed to do that. And additionally, it's not touching real data. It's touching aggregated, summarized data. It's a reporting server. So that's another difference. Let's keep going. Yeah, so let's see chapter 4, easy peasy. Got through that. And again, I have tons of resources on the database stuff. I can talk about databases all day, but as long as you know the basics, I think we're good. Okay. Now, so supercomputers are one of those things where, how do you draw the line between a supercomputer? I mean, these 4090 GPU cards often have more processing power than supercomputers of 5 years ago, and you can get one in your home computer. So it's really hard to define what a supercomputer is. I've built a couple of supercomputers in the past, and just keep in mind that, hey, what are supercomputers to one person might not be the same thing to another person. Let me pull up those 4090 specs really quick. Okay, so check it out. So this is a 4090. They just came out with a newer one, a 5090 maybe, but this gets around 82 teraflops. Okay, that's a lot of power. And then I found this, and this is an older version, so this is a 4070, which is not nearly as fast. It says that, hey, yeah, an RTX 4090 is greater than IBM Blue Genie from 2004. So let's see if we can find a picture of this thing really quick. Yeah, look at that. So my video card, or a lot of people have these video cards. A lot of these video cards are faster than all these computers kind of built together. It shows you how fast computers are changing. So just kind of keep that in mind. When we take supercomputers, we say clusters. Each of these kind of mean separate things, but they're not always the best terms to use. So let's dive into clusters a little bit really quick. So a cluster is just a collection of independent computers, or independent hard drives, or independent somethings. Generally, they're full computers. So each one of these nodes, that would be called a node right here, would have a CPU, would have RAM, and would have a hard drive. Now, granted, there might be another hard drive attachment somewhere else, but each one of the nodes at a minimum will have that. And each one of these will generally have 2 or 3 computers in it. Well, 2 or 4 computers, maybe 8. You pull these things out and they're very, very long. So this might have 2 nodes. This node, or it depends on how you want to break it down, but this node might have 2 computers in it. It might have 4 computers in it. So you might be looking at 80 computers here. Okay, so that's kind of what a cluster is, a collection of computers. Okay, let's move on here. So when we think of traditional computers, we think of a localized file system that's on your computer. Just like Windows, Mac, Linux, things like this. However, the problem is, what happens if we have a really massive file? Terabytes and terabytes and terabytes, or exabytes, something very, very large. Or what happens if we have to have multiple people, multiple CPUs work on a file? Localized file systems don't always really work that well in those situations. When I open up an Excel file, other people can't work on it. So this is where DFS, distributed file systems, kind of come in to play. Hadoop is one we'll talk about a little bit in this class. Hadoop, or other distributed file systems, there's many of them, are designed that you take a file and kind of either break it up, or it can be different parts at any one time. And there's a system, a method of tracking that file. This has become particularly useful in larger files, like video systems, for example. So, yeah, and again, designed not necessarily to be locked on a process. If you have a huge file, if you have a huge Excel file, something that's bigger than you can imagine, and you need to update the first 10,000 rows or first million rows, you don't want to lock the whole thing. You just want to lock the first million rows. So locking, if you don't know, locking is simply the process of, hey, when you open a file, you're the only one that has access to that. We do that to prevent two people from making a change that would conflict with each other. So now there's a term, sharding, and there's another term called replication. So we have a database, a set of data. This is, I don't know, like products and the price. Sharding is the process of kind of splitting that data based on something. First 10,000 rows go here, second 10,000 rows go here, third 10,000 rows go here. I'm doing this at work right now on a data set that's very, very big, and I'm breaking it basically by location. It's not necessarily the best way to do it, but it's just really easy for me to do. So the advantage of sharding is that now you have a bunch of smaller products, much smaller tables you can work on. Make it more reasonable to process, making it more equitable to work on. Sometimes loading a data set can take a really long time just to load it, not even to do analytics, to do anything. However, if you have a shard of something under 10,000, you just load all that data, it could be almost instantaneous. So that's one reason that we do sharding. Now, replication. Do I have a slide on replication? I do. Okay, so replication is a method of copying at the it can be at the transactional level, or it can be at a time level. So we add a line to a master database, and we replicate that on a backup database. Now, when we do this, there's a lot of advantages. It's an expensive process, and I can go into that in a second. But when I have that replication, I can query that replicated database. Okay. So, so like I said, there's a couple different ways to explain this. So I have a database, and it has just a ton of data, or I have a file. It doesn't really matter for this lecture, and I can just copy it to another location. Once I copy it, the copy, not the original, the copy I can work on without affecting the original. Okay. This is a replication. Now, in the database world, there's a couple different types of replication. The two major ones I can think of off the top of my head are transactional replication. Whenever anybody writes one line, it copies that to another database instantaneously, or with a slight delay, but I mean milliseconds. That's transactional level replication. And there's also replication where, hey, at night we kind of scan the database, and we scan the backup database, see anything that's changed, and boom, move it over. So now the advantage of replication is, compared to sharding, it's very fast. Now you have two copies of the data, and working on a copy, you're working on the whole thing. So if you need to do indexing, or you need to do sums, you need to do something on the whole set of data, it's much faster because you're not having to put it all back together. The book talks a little bit about primary and secondary. I think they call it master and slave, but primary and secondary is a little bit more modern term. These are from old hard drive terms. We used to have hard drives like 10 years ago. There was a setting on the back of the hard drive. The hard drive had to be set as master. The second hard drive had to be set as slave, because they only used one cable. And since they only used one cable, you had to have this like jumper basically. Now it's more or less primary and secondary. So as I was saying before, you have a primary database, which would be maybe the database actually getting data from the device, a cash register, Visa machine. You have something getting the data in real time. Okay, and yeah, you're going to back this up too, so that's something different. But you're going to replicate this. You have a replication process that replicates it every second. So in theory, this is an exact copy of this. Now let's think about that for a second. The advantages of that is I can work on this database in near real time. So why don't we all do this? What are the disadvantages of this? Well, if this machine costs 100 grand, between the licensing, hardware, server, everything, internet, guess what this machine's going to cost? 100 grand. This machine's going to cost 100 grand. Where if we go to something like this, maybe this machine costs 100 grand, but this one's like $5,000, this one's $5,000, this is $5,000. See the difference? So, but the problem with this is if I needed to do a sum of all the numbers, I'd have to put everything back together. It's very time taking. It takes a long time to redo all that. So, I included this. Your book didn't really go a whole lot into RAID levels, but it helps in my mind. If you can understand RAID levels, you can understand this in a database level. You can understand this in a clustering level. You can understand this in a bunch of different ways. Let me grab my iPad here real quick. One second. Okay, hopefully you can see this. So, let's think about this for a second. Okay, so let's go with RAID level 0. Okay, so RAID level 0, you have data coming in, and you have 2 hard drives at minimum, and literally, first chunk of data goes to HDD1, second chunk goes to HDD2. This is really, really fast, and I think it says it here, fast performance. Why? Because now this guy can be writing, this guy can be writing, so you're getting literally 2x of performance. Because basically, when you do striping, you're taking the data and spreading it over 2 locations. Data's coming in, you got to write it to 1 hard drive, or data's coming in and you could split it out to 1 hard drive here, 1 hard drive here. This would be faster. Let's think about an analogy in real life. You're moving because the end of the semester. Okay, you can move by yourself, 1 person, or you have 2 people help you move. 2 people, I guess it's people, not person. I don't know. This is faster, much faster. Now the problem comes in. This is also more expensive because again, now you have to have 2 hard drives. Not only that, with RAID level 1, if one of the hard drives dies, the whole thing is gone. So if one of the hard drives dies, all your data is gone. Okay. Now RAID level 1, this is kind of like replication. So you still have data coming in, or HDD, and all you basically do is copy everything to 1 hard drive, copy everything to a second hard drive. So there's no performance increase, no space increase, and I guess let's do it like this. It's twice as expensive. So why would I want to do that? Why would I want to have no performance increase, no space increase, and everything is twice as expensive? What's the logic of that? Well, the reason we do that is because maybe I have a bunch of family pictures. That's very valuable. I have a huge report, hundreds of pages I've been working on for the last 2 years, and I don't want to lose it. So with RAID level 1, if I have that data coming in and something happens, guess what? I have 0 downtime. I need to use the second hard drive. Or vice versa. If something happens to the first hard drive, it doesn't matter. As long as I have 1 copy or 1 hard drive left, because I have 2 copies of everything, I'm good to go. You know. Now, a couple of these other ones are a little more. You know, I mean, I use RAID level 5, and that's probably most common. What you'll see in life is RAID level 5. RAID level 5 is basically where data comes in. Let me think about how to explain this here. So one HDD with a second hard drive. You have a third hard drive. Okay. So what you do is when you have data that comes in, you write part of it here, you write part of it here. Then what you do is on this drive, you keep a mathematical formula of the difference. Okay. So for example, if the first hard drive, for example, all the data came in as a 4, the second drive came in as a 5, well, you'd put 9 here on the third hard drive. The next chunk of data maybe came in as, I don't know, 3. This one came in as a 6. Well, that's probably a horrible example. 3 and 3. So you'd write a 6. Okay? Now, what happens is you get twice the performance increase, kinda. You get more space because, again, now you have 2 hard drives doing the work. So it's like having an extra person to help you. But now if something happens, this hard drive dies, what we can do is we can kind of use math and say, hey, 9 minus 4 on the new hard drive, we need to put a 5 in here. 3 minus 6 is 3, so when we go to rebuild that RAID, we can kind of figure out that hard drive that got messed up. Striping plus parity. And this type of thing that you'll see the same thing in databases. You know, it's all pretty much the same thing. Yeah, your book talked a little bit about, I think, centralized database versus blockchain. Your centralized database is like just traditional databases where, you know, we have one database. Maybe that's not the best word. We have one file system, one server, and that holds all of our data. And that's a traditional way to do it. That's probably 95% of the databases out there right now. Now, blockchain has presented a lot of really neat storage ideas. Okay, so here is the unitary planetary file system. And I can put links to this. But in a nutshell, you know, I don't know if you've used BitTorrent or Tor network before. Basically what happens is you have a file and yeah, it's given a content identifier, okay, like a unique ID in the world. And only that file can have it because it's a mathematical combination of that file. Then either you upload it, somebody uploads it, and that content gets shared around to different people, maybe either as a whole or as chunks or something, you know, like here, you know. And then from there, that chunk which is shared can be reassembled by somebody requesting that, okay. Now, there are a lot of advantages to this. There's a lot of disadvantages, but let's just think about the advantages for a second, okay? Whenever anybody uses a database, it's always logged, not always, but I should say it's logged, tracked, and there's one central point of failure. When you're dealing with either a blockchain or some type of distributed file system, the data does not live at any one place. So it can never truly be tracked, it can never truly be destroyed. I mean, if it's only on 2 nodes, you take out 2 nodes, it'll be destroyed. But often, you know, on something like BitTorrent or, you know, things like this, there's thousands of copies all over the world. Okay, if I'm looking at U.S. News and World Report or something, and I download some data, and I'm sort of reading the article and I have that data in front of me, and I have some type of distributed file system, my neighbor downloads it. It's faster and more practical for me to kind of give him that in an anonymous manner than to have him go to U.S. News and World Report and kind of download it all at the same time. This also comes into where there's copyright problems. Because again, you can't, there's no control access. If somebody puts something on some type of distributed file system that other people don't want, it's really hard to remove it. Okay? So it's just kind of good to conceptualize having one central point versus a bunch of blockchain or some type of distributive file system. Now, yeah, I have a little to do here. I need to go into a little bit more detail on how much we're going to go into vector databases. But basically, what happens is when you take a number like this, okay, so a traditional database would say, hey, here is whatever file this is at, here's the location, it would store it would normalize the data. File, the location, who has access, blah, 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 and things like this. Well, when you start working with machine learning, you get these really long strings, really long vectors, okay? And these really long vectors, can't find the best example, and I don't know really how important vector databases are, and to explain the whole concept of database, because they're relatively new. But kind of the best way I can think of it, or the best way I can explain it, is that there are a special type of database. I think Neptune, I can Google it and find a couple of instances of you. But if we have a vector, so any word or phrase or data can be represented by numbers. Well, somehow we might want to take that number and store it, or that word and store it as numbers. So, Richard, my name might be like 0.5, 0.5, 0.5. Well, then Rick might be 0.5, 0.6, and 0.8. Or Richard James, or that's not or Ricky, better example, Ricky might be 0.4, 0.5, and 0.8. So now we need a special database to take those numbers using special algorithms. Do I have that on here? Oh, I should put like special algorithms to kind of look at the similarities between those numbers. We can go into vector databases. I don't think your book covers it at all, but they're very becoming much more popular right now. So your book does cover Cap's theorem, okay? And there's a better way to explain this. The way I learned about it is 10 times better than this, but let's go over this real quick, okay? You have consistency, availability, and tolerance, okay? So you can't have them all, because if something is available all the time, you basically can't scan it. You can't fix it if there's errors. If it's available all the time and consistent, again, you can't scan it. I guess that's the best way to explain it. If you have a tolerance, you have partition tolerance and high availability, it's not going to be consistent all the time, because, again, if there's unwritten things, you have to kind of purge them out. Okay? So this is Cap's theorem. You can read about it in the book. You can Google it. It's important in databases. It goes back to CRUD, things like this. But now, the way I learned it is the iron triangle. And as soon as it's as dumb as it sounds, anytime you're working on something, you can have it cheap, fast, or good. Very rarely, if ever, you get all three of it. If you have a project or homework and you need it good and fast, not homework, but if you have a project or work, if somebody needs something good and fast, it's not going to be cheap. It's going to be really hard. If you want a mansion built and it needs to be a really good mansion, it needs to be done really fast, it's going to be expensive. If something needs to be done good and cheap, people are just going to take their time. It's going to take a long time to complete. If something needs to be done fast and cheap, it ain't going to be good. They're just going to throw it together. So in my mind, I'm always kind of thinking with Cap's theorem, kind of the same thing here. We can have data that's always available and always consistent, but we're not going to always have that partition tolerance. We're going to have things that's always available, and we're always going to have partition tolerance, but it's not going to have consistency because we can't scan it, we can't check it for bad data. Oh, you want that book? You want me to write a book? You want me to do that book that's going to be a good book? And you want me to do it over this week? It's not going to be cheap. I'm going to have to drop everything, and it's going to be good and fast, or cheap and fast. So always kind of think about this when approaching a project, when approaching anything. Sorry, these shouldn't be in here. Let me delete them real quick. There we go. I removed that. Yeah, originally I was going to go into examples of this and Cap a little bit more in detail, but I mean, you can Google it, and if you get the basic idea, you're good to go. So ACID refers to a unit of work. We were talking about Cap's theorem. This goes back to it, and so does CRUD, which I think is Next. Okay, so ACID basically defines when something has to be updated, changed, or there's a unit of work involved. That's the best way I can explain it. Okay, so if we call somebody, you know, if my phone number is 702-123-45678, it's 8. If I dial half the number, 702-123-45, and I forget the last two numbers, the phone's not just going to randomly connect me to somebody. I have to dial a complete phone number or no phone number at all. I mean, even if I dial a wrong phone number, it's still connecting, but it says, hey, you dialed the wrong number. If I dial half a phone number, nothing happens. This is the basic idea that, hey, the entire transaction takes place or doesn't happen at all. If I run my credit card and make a transaction, it goes to get written to a database, and for some reason the power goes down, internet dies, either that whole transaction gets written to the database or none of it. Okay? And this is super important right there. Consistency. The database must be consistent before and after a transaction. So there can't be maybe bad data in there. That you know, there's states of the database, and you know, you can't have wrong. You know, if you're writing the price of a transaction from a Visa card, you don't want to have the name of the person. That would be an inconsistency. I had a project just recently where I was working on a ton of data, and for some reason, around like, I don't know, 3 or 4 million rows, my data started shifting. I had an inconsistency in my data. I said I had 4 rows, but for some reason the identifier got to the second row. Then after about, I don't know, 10,000, went to the third row. I had some bad data in there. Okay, so again, the whole transaction happened, it just somehow was inconsistent. Now, isolation is the idea that I'm not locking everything. I'm not locking the whole database. I'm not locking the whole table. If I have to write to a database and I write the amount that a person was charged, for example, in a Visa, I don't want to be able to prevent all other charges from happening. That would be very bad. So that your unit of work doesn't interfere with anyone else's unit work or units of work before and after that. And then durability. To what transactional consistency understanding, there's often about, yeah, you can't generally have all of these because, you know, like cheap, fast, or good, everything's kind of a trade-off. Okay, so that I kind of put that in there. So I think maybe your book talks about, maybe it doesn't. So let's see what's next. Okay, so now if we go back to Hadoop, and you know, again, we'll talk about Hadoop a little bit more, but we have a distributed file system, okay, and this is a great little picture. So we have this B1, B1, and I think B1 over here. So we have one big file. You have to kind of imagine we have one big file, millions of rows, and I cut it up into, what's the highest number? Eight sections. And then for some reason, node 1 dies. Well, since I know I have consistency, since I know that my data is being spread over, let's just kind of imagine I'm using a RAID, and my data is spread over a bunch of different places. I lose node 1. There's some type of log somewhere that says, hey, B1 is also at node 3. It's also at node 5. B3 is also at node 3, and B3 is also at node 7, and B5, and so on and so on. So that's why consistency, that's why the CAPS theorem, that's why RAID kind of all plays together. Because there's a video, I don't know if it's in this lecture, I think it is. Somewhere in here I have a video, and it's off YouTube, it's gone. And I didn't back it up, and I'm sure it's somewhere else on the internet, but I'm not going to look for it. But you see the problem. Sometimes servers go down very often. Sometimes databases go down. Sometimes hackers go down. There's all types of problems in the world. So you have to kind of figure out, how valuable is this data? Do I need a real-time copy of it? Do I need a delayed copy of it? How long is my fault tolerance for problems? Okay. I'm going to cover Hadoop. I don't think we're going to do a real Hadoop demo or give you a real Hadoop project. I did Hadoop in this class a couple of years ago, and it was a nightmare for a lot of students. The job offer I'm going to talk to you about and kind of explain the logic of it. They use Hadoop too. Now, Hadoop, in my opinion, and I could be wrong, I don't use Hadoop a lot. I use it when I need to. Just like, the one way I can express it is like driving a U-Haul van. I know how to drive a U-Haul van. I'm probably not very good at it, but I can do it. And that's, because again, in the world, there's people that use Hadoop every day and are just geniuses at it. But, if you know basic Python and you're pretty good at computers, you can use Hadoop. And there's people out there that will help you. So thoughts, questions? I'm going to continue a little bit on chapter 6 because we still have a little time. It's been about 15 minutes. So I do want to keep going. Give me 1 second here. Okay, so chapter 6. The idea of a parallel and distributed. Because again, these terms can get so confusing. I understand that. So when we process something in parallel, we're using more than one core, but we're generally working on a single computer. Not always, but generally we're working on one single computer. When we do something in parallel, when we do something distributed, we're taking it like a supercomputer, we're taking that and we're using some type of scheduler, and we're using multiple computers. Now, sometimes we may think, hey, distributed sounds so much better. I want to do everything on a distributed network. The problem is, let's start thinking about this for a second. Now, you have to find a way to split that file up into multiple chunks. You have to figure out how to install that software, packages like Python, like NumPy, or Pandas, or R, on every computer. You need to make sure that your environment is the same, what you coded on, as what you're distributing the data to. So what do I mean? So let's say that I use NumPy, okay, or Pandas. Pandas is a great example. And I'm using Pandas, I'm coding, and I have this thing working really well on my local computer. I run it on my local computer, it's going to take weeks to run. So I parallelize it, still going to take weeks to run on my local computer. I know, I'll upload it to a supercomputer and have them run it. So I upload my file, I upload my code, I start running it, and boom, it doesn't work. Well, out of the 22 nodes that I selected to run my code, maybe 3 or 4 of them don't have Pandas in it. No problem. I write a script now they all have Pandas. I keep running it, boom, now they don't have NumPy. So running on a cluster can make things more complex. Also, remember, things inside a computer tend to work faster than if you have to go outside a computer. Okay, now maybe 20 or 30 computers might work faster than one single computer, but again, that's just because you're throwing more compute at it. And again, if a job can be run on a single computer and maybe take a day, it might be better to run it on a single computer. Maybe on a week, it might be better to run it on a single computer. If on a distributed system, I've done tests a couple of years ago where I took a job that took, I think, 8 hours on my local computer and ran it in parallel on a cluster. And I think 8 hours is, I think, where the breakpoint was. About 8 hours, I could get it done in about 16 to 18 hours on a distributed supercomputer. Okay. But once I started doing 10 hours on my local computer, the distributed computer, there was a break-even point. So, and I know it's kind of hard to explain again. It's just something to think about. Distributing things isn't always the fastest, easiest solution. You have to kind of think for yourself, hey, is this better to run locally, or is this better to run on a distributed network or distributed cluster? A lot of times too, it comes down to memory too. That's a good point to think about. So while you can have a computer, a desktop computer that have maybe 300 or 400 gigs of RAM, maybe even half a terabyte of RAM, it's not uncommon for distributed supercomputers to have terabytes and terabytes of RAM that you can use, because you can pull them all together across multiple processors. Again, it's not as fast as having RAM on your local machine, but sometimes that aggregation is worth the cost of a slight performance decrease. I'll go into this a little bit more next week or make a video, but Hadoop, the distributed file system, basically it's very simple. You have a big chunk of data. The map basically takes that data and cuts it up. And it has a key value pair, like a dictionary, another term for it. Basically, you have two chunks of data that says, hey, here's this chunk and here's what belongs. You have somebody with a server or a process that keeps track of where all those chunks are. You saw that on that last kind of B1, B7. And so now you have this distributed data set. And then you kind of reduce it where you kind of make it back down to one data set. So this is kind of similar to, when we talk about databases and distributed versus centralized databases. So here's one central big file. We're going to take it and break it up to a lot of different places across the internet or across the network or wherever. And then we're going to place it back together once we do something to it. Here's that video. So upset that it doesn't work. So if we look at the, they use manual vote counts. Do I have another analogy? I do. I think that's a little bit better one. So let's go into this one a little bit better. This is a little better analogy. So we have to go over the lead library to count all the books. That would be a painful task. Can you imagine counting all the books at lead library? I wouldn't want to do it. But what we could do is we could get all the librarians that are responsible for each section of their books. So maybe our, Patrick, who does like the business stuff, maybe he can count the business books. Maybe a few of the other librarians, the health science librarian can count her books. The, fine art librarian can count her books. So we take all these librarians, let's say we have 30 of them, and they count the books in their own section. Now, just to be safe, because we always have that one or two employees that are just to be safe, we have a couple of these librarians count other people's sections too, or at least part of it. So the business person is going to count all the business books, and he's going to count maybe 10% of the fine art books and 10% of the health science books, just to have some redundancy. The health science librarian is going to count all the health science books and maybe 10% of fine art and maybe 10% of, whatever, the anthropology books, okay? So now we have some type of redundancy too. Now what the librarian needs to do, each librarian, they need to take their count, hey, J.R. Token, I have 6 of her books. Richard Young, I have 3 of his books. Michael Lee, I have 2 of his books. And they're going to kind of compress it down to that format. Okay, give me a second. Let me switch over to my iPad so I can kind of show you. Okay, so we have, what is going on here? The business library. We have the fine arts library. We have the art library. Instead of fine arts, just regular art, okay? Then we have the librarians, and the librarians are literally just going to go book by book by book by book by book by book, and they're going to say, hey, this book is written by Young, or Richard Young. I have 1 book. This book is counted by Mike Lee. I have 1 book here. Oh, hey, look, there's another book by Richard Young. Here is a book by Fonseca. Here's a book by Paul LaPlante. Oops. Paul. 1. And then what the business librarian will do is take all this data and summarize it. Two books. Michael Lee, 1 book, and so on, so on, all. Then they'll take all this, the fine arts library, the arts library, and they'll take this key value pair right here, and let's say the FA They have, I don't know, Jones has 3 books. Um, Peters has 2 books. So then they'll send it to a reducer. And then this reducer will basically take it and make a master list of everything. I know at first it's kind of hard to understand, but that's literally the best way that MapReduce works. We take a huge task, you kind of find a way to break it up. You break it up in a very manual process. Then once you do that, you kind of summarize it. Then once you summarize it, you take that summary, that key value pair, it's semi-organized, and you give it to the head librarian to get a master list. If you have questions, I can go into MapReduce a little bit more. We're going to cover MapReduce in more detail next week, so don't worry. I just kind of want you to start thinking about it. Okay, so now the next, I don't know, 5, 6 slides are just tips I thought about over the last week to 2 weeks about dealing with some big data problems. Okay, so you can have large files or you can have small files. Sounds dumb, but if I was to give you a CSV with, one second here, let me see if I can find one. This is about the best we're going to get here. Okay, so hopefully you can see that. Let me see if I can zoom in a little bit more here. Okay, so here is a recipe, or here's a data set with 2 million recipes in it. Okay, oh, there we go, it's right there. So now, I can hand you that one file, and it will take a while. You can't open it in Excel, but it will open in like Visual Studio Code. I mean, it takes a while. I might run out of memory. But you hopefully can open it, you can grab it, you can throw it into Python, you can work with it. Now, you can zip it up too. So, I mean, this is 2.5 gigs. I zip it up, it goes down to 650 megs. Much nicer. But now we can also, yes, we can open it. Another thing we do is put a bunch of small files. Now, a bunch of small files we can open up repeatedly. Just boom, boom, boom. To 1K or 10K. We can kind of, shard it in some ways if you want to think about it that way. Take that large file and break it up. Now, let's think about that. There's pros and cons. Having a lot of small files, a lot of times antivirus software or security software has to scan every file. Also, when you have a lot of little files like that, you're using a lot of overhead. You have to open a file, maybe write some type of header data, close it. There's a lot of overhead. Okay, so a lot more writing small files. So again, pros and cons of each one of them. You can compress a bunch of small files. I have a bunch of scripts to take thousands of files and compress them. But it's just not like right mouse click compress, right mouse click uncompress. Now a large file, if you're importing it, let's say you want to use Tableau or Excel or whatever, and you want to dump that whole file into a database or something, if you get an error, it can be a nightmare to locate. I had one a couple days ago, and it took me so long to try to find out what file was bad or what row was bad. Let me rephrase that. I was importing 5.1 million rows into a program, basically Python to process it. One row had some weird funky data and it had some special character. I think it had an emoji. And it took me forever to find it. Okay. Now, one solution was I could break all 5.1 million rows up into individual 5.1 million files. And I just start processing it and deleting each file after I process it. Well, as soon as it dies, I know exactly the top file. I know exactly where the problem is. So small files would be much easier to debug. Okay. So, you know, I can't stress this enough. You know, when you're working on projects or data, you know, think about how, you know, you're going to receive that data. Think about how that data is. Is it one large file, a bunch of small files? And you can go back and forth. You can concatenate them to get a bunch of small files to be one large file. Okay, so what else? Also, when working on supercomputers, and I kind of alluded to this, maybe I should have been more clear, but between parallel and clustered, or between data sets, you always have to think about what is your slowest link. Okay, and what do I mean by that? Okay, so if I have a 2.5 gig file, let's see how long it's going to take to zip up. Desktop, zoom. Okay, so here's that big file. So my goal is to work on this file or something, so I am going to zip it up. Because I know if I zip it up, I can send it over to my friend much quicker. We'll just use 7-zip. Okay, so it looks like maybe a minute 30 to zip, maybe a little longer. But now, if I have a fast enough internet connection, and it takes only 30 seconds to send it, zipping up is a waste of time. So you always have to kind of think about the slowest process in the chain. Now, we see it's still, now we're at 140. Is how long it's going to take? 1 minute, 40 seconds. I'm going to pause the recording for a second. Okay, so now we're getting close to the end. So let's just say it takes 2 minutes to zip this 2 million recipes. Okay? I mean, we're over 2 minutes right now, but let's just say it takes 2 minutes. So how long does it take to copy to an SSD? Or let's say how long does it take to copy over the internet? I have a network drive. How long would that take? So we're at let's say 220. So let's see how fast it takes to copy over to an SSD drive. So yeah, 2 minutes and 30 seconds to zip this up. Okay, I don't know why it's taking a while. So there we go. So recipe data, the same file. I'm going to copy it right here. I guess it copied so fast I didn't even see it. Yeah, literally, I have a program that kind of measures it, and it was like less than 2 seconds. Okay? So, now. So this is one of my slower connections right here. So let's see how long it takes to copy. Where is recipes? Explorer. So, about 20 seconds. So you see that there's really no benefit to compressing this small of a file. It took me 2.5 minutes to compress it. And you know what? If I compress it, instead of taking, what's it take, about 20 seconds to copy? Something like that? If I copy this, so instead of taking 20 seconds to copy, it copies in 5 seconds. So, you know, so 2 minutes and 5 seconds of processing, you know, that's just not worth it. Okay, let me delete this. So always think about the slowest link. And I know that's kind of weird, and you might not always know it, but after a while you start thinking about it. Hey, is there a way that I can take this memory, copy it to my local hard drive? You know, is that faster? You know, can I take this chunk of data and move it to a RAM drive? Or is it the CPU? Is it just my CPU that's running slow? Or is it the hard drive? You know, so if you have a supercomputer, but it has a really slow internet link and you have to access the data on the internet, it's not going to be much faster. You know, so kind of always think, and the book doesn't really go into a lot of detail about this, but always think about what the slowest link is. Is it a CPU? Is it memory? Is it the network? You know, because sometimes, you know, like if I zip a file, what's definitely going to be faster to transmit? That's not always the case. Maybe it's not. My video's not playing very good. Weird. So, last semester I went through half of this before really defining what MVP is. And I love the idea of MVP. When I started in business, I knew what it was. It just didn't really dawn on me what MVP means. MVP is minimally viable product. It's a part of agile, I guess, development. The idea in programming is really what is, in tech, you hear this thing, move fast and break a lot of things. Okay, that's MVP. MVP is what is the minimum requirements to get the job done. And why is this important? Because we want to make sure that we can get the job done because we can go back and fix it and make it better. So, I had a project on Wednesday, where basically we're trying to collect a lot of data. Okay, we're trying to figure out if a certain medication makes people lose weight, makes people gain weight, what happens after a year, what happens after 2 years, what happens if they stop it, how does the cost affect it. So, literally, what the plan is, we had a whole meeting about this, is that, hey, I'm going to collect a certain data set, name, patient, MRN, when they started the drug, certain labs, blah, blah, blah. And maybe like 10 rows. I'm going to get that done really quick, next week or so. Then, as we're going down, I can add more data to that as we need. I can add more data to that as I need. And this is the concept that just eludes so many people. Okay, let me go back to the class and explain this again. Okay, so if you know that we don't accept discussions late, where's discussions are here? So this is due Sunday night, which I think is tonight. If I was to post on Monday or Tuesday, I get 0. So maybe it's better to post something, even if it's not perfect, and get some credit than not post anything. I can always update it and fix it. I mean, we can go in here and hit edit post. Okay. This is the idea of MVP. I want to make sure that this basic core concept is driven home in you guys. It is so vital. And, I knew about it, but it never really hit gray matter for, 5 years, I guess, of working. I try to make every project perfect, try to make every data pull perfect. I was trying to over-engineer for the next 10 years, and it just never worked. So again, the idea of MVP is what is a minimally viable deliverable? What's a minimum but often, okay, it's weird the way it broke that up, but often we can do better. But so, MVP is just, hey, get the bare minimums done, get it done before it's due, and then you can update it and make it better. Okay? And this is especially true with big data. This is especially true with a lot of things in big data analytical processing. Okay? Let's say that you want to do an average, okay? But there's outliers. Well, first, let's just get the average working. Here's my average. I know there's outliers. I know I've got to fix that. But hey, you know what? I have an average here, and tell people, hey, my average is not right. It's not great, but I know it works. Then next week I can go in and say, hey, anybody that's outside my IDR or so however you want to get rid of your outliers, you can shave them off. But here, I have the average. We can make it better next week. Instead of say, hey, you know what? I spent 2 weeks figuring out the best method to get rid of the average or to get rid of the outliers, and nothing ever got delivered. This is a key concept, so please remember this. Now another thing too. Where's my phone at? I cannot believe that this has just been so fundamental. So here's this. See if you can see my phone. Let's see there. So, too much data. Okay, so I use this all the time. Okay? So, when you're working with supercomputers, when you're working with large clusters, when you're working with large data, you do things that could take a day, 3 days, 4 days, 5 days. Let's say you have 2 computers at your desk. The one that you do your email and all your stuff on, another one which you just run huge jobs on. It doesn't matter if it's a supercomputer, it doesn't matter if it's an old, Intel from 10 years ago. But when it's done, instead of keep checking on it and always check in and always, you can have that machine basically text message you if there's an error, or text message you if it's complete. And it's super simple. And it's funny, I've never really seen books talk about this. I've seen this in one conference, and I was actually shocked. So this is super helpful. I don't care what site you learn to use in your career. I use TextBelt. It's super cheap. I don't even know what it is. TextBelt, like $5 or something. Pricey. Yeah. So for $5, I get 200 text messages. Okay. You enter your API key here, which is this. I put a bunch of X's in mine. So basically, what happens and how I use this. Okay, and I can send you the actual code if you want. Basically, when my Python runs, once it gets to the last cell, it shoots me a text message. Or if there's an error, it shoots me a different text message. This saves my life all the time, every week. I know that, hey, I can walk away. I can start a job on Thursday, which I did this week. I started a data pool this Thursday on a machine. And I don't have to worry about it. And then Saturday night, I got a text that says, hey, the job's done. So I'm surprised that more people don't use it. So when you're dealing with big data, it's always important to find a way to monitor your process. There's a program in Linux called Screens. You can do it. This is just, for me, 90% of what I do is in Python. But I mean, you can do this in Tableau. The demo I saw was in Tableau. Somebody put this on a Tableau or Alteryx notebook, and when it was done, boom, it just shot them a text message. Okay, so find a way to somehow have an alert. It can email you, it can text you. Somehow, when a job's either done or error, it needs to let you know. And you'd be surprised how many books don't cover this. Next week I'll talk about this. Okay, so. Okay, it's rare that I get an opportunity a job opportunity at the same time I'm teaching a class about the topic. So let me look real quick. So this was emailed to me Thursday, January 18th at 8:43 a.m. Okay, so let's talk because, so from what I understand, I talked to the guy that was hiring for this. So what they're looking for is somebody that creates these sustainable reports. I'm not really sure what they do, okay? But if you look, a lot of it is BS here, okay? So blah, blah. So you can work anywhere remotely, okay? I work half remote, half in person. Yeah, so you'll be basically working on a Dow Jones Sustainability Impact Report. That's what he said. Okay, so blah, 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 blah. Nobody cares. So 3 years of conceptual data analytics to formulate hypotheses and determine assumptions to test and interpret data. I talked to the guy, he's like, don't worry about that. 3 years of providing analytic interpreting data. So those are just basic analytical skills, basic like sums, what happened, things like this. 3 years of using using Excel. I told him, dude, I'm not great at Excel, but I can do a VLOOKUP, but nothing great. Database management experience with SQL. He's like, you don't need to run a database, you just know how to query a database. Then Tableau, Domo, which is another product of Power BI. Okay, I'm like, okay. So when I talk to this guy, let me see if this thing's still connected. Let me kind of explain, I think, what we're looking for, because this is so relevant to what we're talking about today in class. Oh, and let me just make sure, healthcare industry, blah, blah. Yeah, and he said it's going to be like 120-ish in that range, okay? So remote, blah, blah. So there's a job. So let's talk a little bit more in detail about what you'd really be doing. Now this is just one of a million jobs out there that are like this. Okay, so let's find a nice blue, black. There we go. Okay, so job info. So when I talked to the recruiter, basically what he said is that they have a Hadoop cluster, Hadoop data set somewhere. Okay, and that once a year I run some code. I already have that code, but I just run it and I get a really, really big data set, I guess. Okay. Takes, I guess, a couple hours, a couple days to run. And basically what I get is all the people that have taken classes at Optum or United Health Group, all the people that have done volunteering hours. I mean, we have, let's say, 300,000 people, employees. And so you're going to say, hey, I mean, me personally, I've taken 20 free classes online. So you're going to get a big aggregated data set of, maybe how many classes each person took. I don't know, number of classes. maybe number of hours in those classes, maybe if they have a PhD, they have a master's, they have a doctorate degree. Maybe I'm assuming basic demographics like that. Okay, so you run this Hadoop script once a year, maybe twice. Maybe run it before you actually run it, and you run it. Then what you do is you take that data and you basically, I guess, put it in Excel. Basically, clean it up, and to do some basic formatting. Okay, so you have this massive data set right here. Okay, maybe terabytes. I have no idea. Then you do some magic on it. They give you a script, and then you get it down to maybe a gig or however big it is in Excel. Then from there, you take that Excel and you put it into Tableau. You make pretty charts. Okay. Now, we talked about data, information, wisdom, or knowledge and wisdom. This is a bunch of raw data. That's what Hadoop is great at, processing these huge chunks of data. Now, Excel, maybe we can get rid of people that aren't in the non-US citizens. Maybe they only want US citizens. Maybe we get rid of people that are no longer working. We got most of the data here. We just want to fine tune a little bit. Now we want to know what subject areas are people learning in 2023 versus 2022. That would be, something like this. What has changed over the last couple of years? Where can we invest more funds to help our employees grow? This doesn't give me that. This doesn't really give me that. Tableau does. Okay. Just let me go back. Where is that? So enterprise talent development and learning. They're developing tools to drive decision making for business performance, providing executive insights and key trends. Go down past all this stuff. Blah, blah, blah. So 3 years of experience doing testing. Well, how do I do a test? Well, if somebody says, hey, are we doing more AI training? Well, I can look at 2020, 2021, 2022, and 2023 and see if there's a growth in classes related to AI and machine learning or something. In Excel, maybe you need to do some type of VLOOKUP. Say, this class from this provider is the same as this class. I'm not really sure. SQL, that way maybe you can figure out what level each employee is at. This person's an MD, this person's a nurse, this person's a PhD. That's why you might need the SQL. And then finally, let's present this. Let's show somebody that can say, hey, you know what? The nurses seem to like a lot of these COVID vaccine training. So we're going to spend a lot more money getting them more training. The salespeople tend to like these classes on how to use Salesforce. Okay, so then once we get all this data, we put it into knowledge, something like this. And again, this was just Thursday, 2 days ago, 3 days ago, and something like this came up. So these are real things that people are looking for. Okay, hopefully that I don't want to say gives you hope, but these are important tools I'm teaching. I'm hoping. So I haven't released the ideas on the research proposal or research topics, but as you're reading in the next couple of weeks, I want you to keep in the back of your mind, if you could do any research, money was no issue, data was no issue, what would it be? Here, I got an example. I didn't even think about this. Give me 1 second here. Okay, so one of my very favorite interesting things that I've always wanted to do research on is the comparison of these sketches. These are sketches, sorry they're so small, between people with Parkinson's and people without Parkinson's. Healthy. And you can see, I mean, visually, you can just use your eyes and see the difference. Okay, so, I mean, if I had unlimited time, unlimited money, that's something I would dig into. I'd have to first make a bigger data set of that. Then I could create some type of application, which I'm probably going to do over the summer, that actually tracks that. And that would be so helpful to so many people because patients would be able to do a little test and say, hey, my drug's working, L-Dopa's working, or it's not working. I mean, it's just something I'd love to do. So I want you to kind of think in the back of your mind over the next couple of weeks. I'll tell you more about this next week, and I'll tell you more about it the week after. It's not due for another month, or more than a month. But if you do any research, what type of research proposal would you tell me? Why would it be impactful to business? Why would it help? That Parkinson's one I can tell you right now. So, 20% of America lives in rural towns. They don't have access to great doctors. That application right there that I could design could give patients with Parkinson's better prescription management. That would save insurance companies millions of dollars a year. Okay? It would prevent hospitalizations. It would allow patients to live longer. I mean, there's all types of reasons, okay? This week, the discussion topic is about data utility versus data privacy. So data utility is how do we use data that we have, and data privacy is how invasive is invasive data. Now, we haven't gone a lot into, how much data you can get in and what's private data. I use an example, and I just thought about this when I was typing it up. Apple wants to scan your iPhotos, or your photo on your phone to look for sexually abusive material. But then issues came up with how do we protect the people that, I don't say that have nudes on their phone, but basically have, naked pictures on their phone from an Apple employee looking at it. Okay? Now, we can prevent people from sharing, bad materials with this technology, but it would come at the cost of people's privacy being invaded. So, maybe go around, pick a topic you want. Some of it's government surveillance. Now they're using Face ID at all airports. Is that invasive? I pick a reference in there about Clearview, which is a program, a company that has 40 billion faces. And basically with 40 billion faces, you can tell if somebody's a criminal or not. I mean, hey, John Wayne here is a criminal. This is what his face looks like. And anytime he goes anywhere, they should be using Clearview, and they can detect every criminal. They can get 99% of the criminals off the world, or off the streets, I should say. The problem is that invasive? When you walk into Smith's, do you really want your face scanned from a video camera? And if it is scanned and it recognizes you as a criminal, do cops just pop out and arrest you? That's utility, data utility versus data privacy. Again, try to really make that first post by Thursday and make a follow-up on your students by Sunday. I'm going to probably post a quick code demo this week. You're not really going to have to do anything but besides run this. I have a couple different code demos. I just want to make sure that if I give you a OLAP link, you can actually run it. So that will be the goal. I know it's low-hanging fruit. If I just give you a link, can you run it and send me a screenshot? Because soon the things are going to pick up once we get through a lot of these fundamental stuff. As I said before, those of you that emailed me or text me, if I don't respond within 24 hours, please try again. I'm really good about getting back to email. I'm really good about answering emails and texts. But sometimes if it goes into spam or sometimes if I don't see it, hit me up. Okay, don't be afraid to harass me. I'm here to help you succeed. I'm a very different teacher, and I believe my only job in life is basically to teach you and to get you to that goalpost, get you to that finish line. I'm not here to go through a bunch of didactic stuff. I'm not here to read out of the book. My job here is to give you some fundamentals, which I know are boring. I'm not going to lie, they're boring. But once I give you those fundamentals, I want to be able to make sure that you have a solid enough foundation that you can grow. Okay, so don't be afraid to contact me. Thank you again and have a great week.